Hey everybody. I hope you've had a good break. I just wanted to come back and do like some code updates for some of the Advent of Code stuff we've been doing. I got some good input from everyone. So in particular today, I'd like to talk about day 14, 17, and 24. The other one I really wanted to talk about was day 25, but I haven't gotten to doing that stuff yet. So I thought I'd just give you an update for those first 3 days. If you have other days you'd like me to go over, or maybe I missed a comment that you had that you thought was effective for some of those other days, just remind me and I'll check those out too. But these were the ones that were on my list that I remember wanting to go back to look at after seeing some of your comments. So again, I love all the comments and the stuff that you're doing, so keep bringing that in, and then I think I have a couple more things of Advent code I want to talk about, but then we'll just move on to like algorithms in general or other puzzles, things like that. So with that, let's get started. So the first day that I want to talk about was day 14. And if you remember, this was the collector dish one where you have like a dish and you want to like slowly roll all these O's up, down, left or right, north, south, east, or west, right? The algorithm that I had implemented for it was like you find each O and then you move it up as far as it can go up and then you stop. And it's Wayne Bagley, I think. Hopefully I said that name correctly. Everyone gets my name wrong too, right? I get iCub3D and all the time, or ICU bed, things like that. It's I cubed, the math number. Anyway. Wayne Bagley mentioned that there's a more efficient way to do that. And the idea is to think about the columns in their own. Just think about when you're rolling north, think about the column itself, and you can kind of track where you can move, where you could move the next O. And then when you hit it, you just put it there. You put it in that place where you're tracking. And then you find the next place you could put an O, and you kind of slowly do that through the list. So the idea is kind of like a slow pointer and a fast pointer. You know, the idea is the slow pointer is the next place you could put the O, and then the fast pointer is like looking for those O's. And so you do that. I think in my code I call it tortoise and hare, but I can kind of show you an example of what it would look like really quick. Imagine like we have a grid here and we're rolling to the top, and we have, I don't know, something that looks like this, we'll just one column, right? Here's an O and then a dot, and here's an O, and then here's a dot, and here's a hash, and here's a dot, here's a dot, here's an O. Assume this is just a single column. You'd kind of have a slow pointer. Let's say it starts right here, and it's looking for a dot, right? The slow pointer is like, where's the dot? Where's my next dot? And then you have a fast pointer that's saying, where is my next O? And so it's going to traverse to find the next O, and eventually it finds it right here. And then we do a swap, right? So we'll say, okay, at this point we do a swap, and so we now have an O right here and a dot right here. And now we want the slow pointer to find the next dot, right? So it's going to move to right here and find the next dot. And the fast pointer then is going to keep searching, right? It's going to say, okay, where's my next O? And eventually it will find this O, and so now it knows it can swap to the slow pointer, right? So it will move the O right here and make this one a dot, right? It will do the swap, I guess is the way to say it. Because it's not just make it a dot, it's an actual swap. There's weird cases where I'll talk about those in a second. But then you have now the slow pointer wants to find the next one, so it's going to go right here. And then the fast pointer is going to start moving and looking for those. And when it encounters a hash, that's a key indicator of like, now I can't go this direction anymore. So what you do there is you then move your slow pointer to above the hash. Oops, that was the wrong color. You want to move it above the hash, right? So you want to say, oh, now my thing is above the hash. And you'll just keep doing that iteratively, right? Whenever you see one, you move it up. But then your slow pointer will start moving and looking for those O's, and oh, it found one, and so now it's going to perform the swap, and so that's going to make that a dot and this one a 0, and then your hash will find the next one, and then you're done with the row. So now this is what the new, right? These are like this is what the new column looks like. Now, why is this more efficient? If you think about what my algorithm was doing before, it would eventually find this and just kind of slowly bubble it up one by one, and then find this one and bubble it up one by one, and then find this one and bubble it up one by one. There was a lot of like slow movement, whereas these are doing like large skips, right? It's saying like, oh, I'm going to move here, I'm going to move here. And so that's happening quite a bit faster. So what does that look like in code? Let me see if I can find the roll faster. P1 faster, here it is. So again, basically I'm tracking my total for part 1, but I'm going to go through each row of the grid, or I should say each column of the grid, and then for each column I'm going to track what is my next. That's like my slow pointer. And then I say, okay, I'm going to go through the grid, or go through now the Y values, right? So I'm going to check each one. And if I ever encounter an O, I need to do the swap, and then I need to find the next place the next valid position for my thing, right? So how does that work? Is I just say next, I need to increment my next, and then I just keep incrementing it until I find a dot, or I get to my fast pointer, right? If I get to the fast one, I know I need to stop there. I don't want to like exceed where my fast pointer is. So that's all you do, right? Is slowly you're going to have a slow pointer that's slowly incrementing, finding the next dot, and you're going to have a fast pointer that's eventually going to find like the next O and perform the swap, right? This is just a way to do a swap, and then find that next position. And this is the special case. If we find a cube-shaped rock, we want to just move the next position to above it, right? And I'm not doing bounds checking here. That's mostly because if I ever hit the end in the Y direction, right, these the values of these nexts don't really matter, because I won't consult I won't use next anymore once I've gone off the grid. And so that's why I can do some shortcuts here with this swapping and this incrementing here, just because I know this is going to keep me in bounds. I'm never going to use this if it's ever out of bounds, because this would never get me there, I guess is the way to say it. So anyway, I also implemented like faster functions for the part 2, and they all again look as exactly the same as P1. The only difference is, right, besides rolling north, now you have to roll south, which is like the opposite way. So your next starts at the bottom of the grid, and instead of incrementing your next, you're going to be decrementing your next. You're going to be subtracting, right? So you need to use saturating sub here, because you don't want to. I'm using U sizes. If you're using another language, an int is probably fine, but or if you decide to use like an I32 and you just want to cast these X's and Y's, you don't have to do this, but I'm using a saturating sub just because in this case, I wouldn't want to go -1. That would cause a stack trace, right? A panic. But they all look the same. It's just a question of how are you tracking your slow and fast, right? Otherwise, they're all really the same. And so if you run it, you can see like the P1 faster implementation is somewhere on the order of twice as fast as the previous implementations. So that's quite a speed up. And I don't think it's substantially more complex to reason about. But you get like twice the speed. So I thought that was a cool little way to, refine the code and make it a little bit better. So thanks to Wayne Bagley for that. And with that, let's move on to day 17. And this one was, if you remember, this was a pathfinding algorithm. We implemented it in Dijkstra. But in short, the idea is you're trying to move this crucible from the top to the bottom. And the only, in the quickest way, what's the fastest way to do it, right? And so you implement Dijkstra to do that. And so you have to have a different neighbors function for part 2, right? For part 1, you can't move more than 3 directions in the same place. Or you can't move the same direction more than 3 times. You have to turn after you've done it 3 times, right? And then in part 2, it was you have to go at least 4, but you can't go more than 10 in the same direction. Like, that's the difference between part 1 and part 2. It's really just 2 differences in your neighbor functions. So they're both Dijkstra. It's just it's what are your neighbors, and that's what you have to figure out. And so Tricky Nguyen 9757 pointed out that my functions actually look really close to the same, and you could actually implement them in one function. And so I did that, right? So if you look at my initial neighbors function, this is for part 1, you can see, again, I'm making sure I'm not going in the opposite direction. And then I can't go in a, well, this is the, if we're going in a new direction, that's fine. If we're going in the same direction, it has to be less than 3, right? So that's the idea, is if we've changed directions, that's fine, but we can't go more than 3 in the same direction. Again, and then if you look here at part 2, a lot of that's the same. All that I've said now is I can't go in the new direction unless I've gone at least 4, and I can't go in the same direction if I've gone more than 10, is the way to think about it, right? So I can only add my neighbors if those constraints are met. And again, you can see these look pretty close to the same. And so I combined it into one function, right? Where you just give it a min and a max. In this case, I used one of Rust's tools, or one of Rust features called const generics. So I'm creating a generic function with 2 const values, the min and the max. And this is just like, if you're familiar with generics, it's like any other generic, except you can say, oh, it's not a type, it's a constant. And so my constant min is a usize and my constant max is a usize. And then I can just check those in these cases, right? So I can only add it if I'm going in a different direction, but I've gone in my current direction more greater than or equal to min. And I can go, if my directions are the same, I can do that as long as my direction count is less than max, right? Like I haven't gone in this direction more than max times, right? So this is, I can change as long as I've gone at least the minimum, and I can go in the same direction as long as I haven't gone more than the max, is the way to think about it. Hopefully I'm describing those okay so you make sense, but I can use these const generics now to specify them. So now if I look at my neighbors let me find it where I'm using it. You can see now for part 1, instead of passing the neighbors function, I just call neighbors combined with a min of 1 and a max of 3, right? And then I call part 2 with a neighbors combined of a min of 4 and a max of 10. And if we run it, we get the same answer as we got before, but now I've used a singular function to solve both of them. It's just a generic function where I provide the min and max values for me. So again, this one wasn't like too much, but it is a cool feature of Rust that I like. Is these const generics. So there's actually, I'll put a link in the description for this page. It's kind of a cool page if you're not familiar with it. that talks about const generics and how they work. And I think it even has some exercises here where you can like play with it to figure out how they work, and how you might apply them to your things to get the correct, like, to get the correct stuff, or I get the correct answer, I should say, for these. But again, I think what's cool about them is, if you have some of these things where you want your min and maxes to apply only in special cases, or in different cases for different parts of your program, you can use them in a generic way. Now you don't have duplicated code, right? So I've potentially taken two functions and turned it into one just by implementing it with these const generics. Okay, so on to day 24, and this is the last one that I wanted to talk about for today. This was the never tell me the odds. If you remember, the idea was you've got a bunch of hailstone falling at different, starting at different positions and going at different speeds. And for part 2 in particular, it wants you to throw a rock such that it hits all the hailstones in a direct line. And my solution was a system of linear equations, right? So I was trying to, given a coefficient and the dependent variables, I could find what those x, y, z, and vx, vy, vz values were to get the answer, right? And we can talk about it a little bit more. But if you remember, my Rust solution wasn't actually giving me the right answer, so I solved it in Python. Gordon 508 mentioned that this is it's likely due to a rounding error of int versus float, right? So one thing Python does is it treats all numbers as like integers, as long as you aren't using like a floating point number, until it has to turn it into a floating point number, right? But because of like some division or something like that, right? They have operators where you can keep using integers, but like essentially it will use an integer until it can't your operation would turn it into a float. That's not the case in Rust though, because we're statically typed, right? So I did find a solution to fix that, and we can just look at that really quick. This is the Z3. We'll talk about that a second. That was something also that Gordon 508 had mentioned. But here is my P2 using linear algebra. And instead of using the ND array package, I use the N algebra package. So that actually got me the right answer switching to that package. It was another one that I tried, and using it tried. So it looks ugly, but here's my dependent variable. And you can see that it's like I'm now treating these floats as I28s, which is a huge number, right? And so I do the multiplication and subtraction via I28s, and I only cast it to an F56 until after I've done all the math, right? For these ones, because it was just simple subtraction, I didn't need to do this. But because the numbers are so large, when you're multiplying like two large numbers, obviously there's a higher probability that you'll get some rounding errors when you're using an F64, and that's essentially what the problem was, right? So I treat them as actual integers until I've done all the big maths on them. And then I turn them into an F64, which I can pass to my solver, which is down here, right? Again, this is just a solver, and I have, I'll provide a link to it. This is the N algebra documentation, but basically you give it your A and your B. So this A are your coefficients, and B are your dependent variables, and you use LU to decompose A, and then you can solve B from A, or you can get X by solving B from that decomposition, right? So, and you actually get the right answer here. So that works, right? I'll show you the answer in a second, but now you actually get the right answer in Rust. So if you're looking for a purely Rust linear algebra thing, I think just the thing to remember from this, I found the nalgebra library for some reason to be more accurate. It actually gave me the right answer. And because we're working with such large numbers, even an I-64 wasn't doing it. I had to do it as an I-28. So this is like it's larger than an I size, right? My I size is I-64 for my system. So this is quite a large integer value. It's like double the size of a 64, right? To do that multiplication is kind of what you needed, these like large things. So once you've done that, though, then you can cast it to an F64 and do the actual work to solve the problem, right? But anyway, that's what gets you there to the actual right solution in Rust. So thanks again to Gordon508 for mentioning the rounding errors that might occur doing those early casts to F64, just because of the sheer size of these like values. And then finally, Gordon508 also mentioned using the Z3 solver, which I think I mentioned that in my video, that I've heard about this before. If I remember right, I'll have to look. Well, let me look and see. We can just look at it right now. I'll give you a link to this. Yeah. So this is it's called a theorem prover, and it's by Microsoft Research. The idea is you give them some variables and you give them some constraints, and it will find a solution to your problem. And I actually want to walk through this code a little bit because I think it helps describe this system of linear equations that you're trying to solve. The linear system resolution, right? What you're trying to solve for in this thing of linear equations, right? These values look ugly, right? These dependent variables and the coefficient right here. This just looks like a bunch of gobbledygook math. If you're looking at the Z3, it will kind of help you understand what you're solving for, what you're trying to solve for. So let's just walk into it. Again, the idea is it's a theorem prover. You give it a set of constraints, and then it will find the values that meet those constraints, right? So this is some setup work you have to do, right? As you're saying, hey, I want to create a solver using the default context and the default config. And then you give it some variables, right? So I'm going to create some variables within that context. And this is my X, Y, Z and my VX, VY, VZ. These are this is the rock's position and velocity that I want to throw it from, right? This is what I'm solving for, you can think of. I want to find these values. And then I just need to put some constraints on it. Oh, I add time values, right? So if you remember, the hailstones are all falling at different velocities, right? So they'll all line up. Your rock should hit them all at different times. Not all of them. Well, I think it will be all of them because it said the hailstones never actually hit each other. So you want to throw a rock, and the time values that you hit each hailstone will actually be different. So that's like the tweaking you're going to do, is you want to tweak the times of each of those different ones such that your rock hits them at those times. And so you want to have those as some variables too, right? You want to track each of those times. So that's what I'm doing here, is I'm tracking the time variables for all of the hailstones for each of these. Now that I think about it, I could have probably done it in here. I don't know why I did it outside. But also notice that I'm only doing a take 3. Again, because of the way that the problem is specified, one key insight is that you actually are only interested in 3 of the hailstones, as long as those 3 hailstones are linearly independent. Just meaning like they're different hailstones, and they're going in like different directions and position and velocities, such that they would properly constrain the solution to the problem. So we can actually put this right in here, I think, if we go go like this, iter take 3. We also want to enumerate. That's what I wanted to add here. And then right here. Oh. We'll want to do pointers too. Is that right? Well, we'll find out if it's right. But essentially, what we're saying here in this loop, we want to do that. We're just going to do the first 3 hailstones. Now we don't need this. For the first 3 hailstones, we're going to add some constraints. And what are those constraints? So this is just I've created a variable for each hailstone's x, y, and z position, and its time position. And what I'm going to say is, again, this is kind of the variables you're solving for. That's why it's a const versus just some, static variable or whatever. This is one of the variables I'm trying to solve for in these, right? You can think about these as like variables, and these are like known values, and I'm trying to solve for these variables, right? The times will be different, and my XYZ positions will be different, but these ones will be constant. And then I can just add those assertions to the Z3 solver. And that's just saying, here are the constraints I want. And so I say my X plus my VX times T is equal to this hailstone's X plus its VX times T, right? Essentially what this is saying is, if I've moved the hailstone to its time t, and I've moved my rock to time t, those 2 times those 2 positions must be equal in the x, y, and z axis, right? This again, if maybe said another way, these 3 lines are saying my rock position needs to be equal to my hailstone position at the given time, this time right here, right? And so if I do that for 3 of the hailstones, I now have 3 different times where each of my rock's position has to be equal to one of the hailstone positions. And now my solver has like all the assertions, right? It says, hey, here's the values you can fidget with, and here's the time that you can fidget with, and I want you to find a value such that that rock will hit these 3 hailstones at the correct t values, right? So it's going to do that solving and find it for you, right? And how does that look in Rust? Well, the Z3, first of all, you need to check. It will run a check and say, is this satisfiable? Which is just a nice way of saying is there a solution to this, right? So it's going to go find a solution, and then if it's got a solution, you can get the model to the solution, and then you can calculate your XYZ values, which is what the problem wanted in the end, right? It's like, once you've figured it out, add up your XYZs and return that value to it, right? So that's what we do in the model eval here, is we evaluate it, and then we can print it out. So again, just at what a high level of what the Z3 solver is doing. And the reason I want to describe this is because you're doing the same thing in the linear algebra model. It's just you can use linear algebra to find these things, right? But you're still, the way the linear algebra one works is you're still kind of putting those same constraints on the t and the xyz values, right? So you've got some variables that you want to give it that it can like fiddle with, try and find the right number for. And so this is like, think about it as your rock position and velocity. And then for each of the hailstones, again, we only need 3. For each of those hailstones, we can create some values, some values for them, and a time variable that we can kind of pass to the solver and say, hey, can you find a time in this case for all of the rocks where my rock, or sorry, for all the hailstones. I may have said that wrong. Let me say it one more time. We're saying for each hailstone, can you find a time where the rock would collide with that hailstone, right? So the rock's position in that time is equal to the hailstone's position in that time. And if you can do that for all 3 hailstones, then you have an actual XYZ value that you can solve for. Okay, and so let's run it and see how it works. Again, here's, so you can see the Z3 solver down here does give you the actual right answer. It just takes about 2 seconds to do it. I guess I could run it in compiled mode. Maybe it's faster. Not much. Release target. So it's about 2.5 seconds, right? It takes the Z3 solver to solve it. That's still really fast if you think about what it's doing. It's trying to find some absurd XYZ value and VX, VY, VZ, where it lines up with those 3 things, right? But you actually do get the right answer. At least for me, it was the right answer, right? Now I'm worried. I should double check. Yeah, I think that's right. Yeah. But here's my using the nalgebra, the linear algebra solution, and you can see it solves in like no time at all, right? In microseconds. And why is that faster? Again, the linear algebra is just doing math to solve it. This one, the Z3 solver is like using the constraints to like build a model, and it does like, I actually don't know how it works on the internals, but I imagine it's slowly like using the constraints, the assertions that you make for each of them to like shrink down the set of values until you find like one that fits it, I guess is the way to say it. But again, I haven't read a lot about how they do the Z3 solver. It is a cool thing though, right? The reason why it's really cool is because you can actually use it to solve all kinds of problems, right? Any kind of problem where you can add some constraints to, and the value may be generic, but you don't have like a, maybe there's not an easy linear algebra way to do it. Maybe you're trying to prove a theorem or something like that, right? And so you can put it through these constraints and it will help you like prove that what you're doing is correct. So I think the Z3 is really cool. Again, it's just a little slow because it's not strictly doing linear algebra. It's trying to solve it. But thank you again to Gordon508 for, first of all, finding the rounding thing, the way that I could simplify this to round it. And for mentioning the Z3 solver, I was able to go do that in Rust. And you can see, yeah, it works. They both work. And I actually have a working solution in Rust. So there you go. Those are the 3 days. I'll make sure and have links in the comment or in the description of some of these things so you can go check them out yourself. And then we'll have an upcoming video sometime on day 25 because I want to actually implement the Stoyer-Wagner algorithm. And someone had mentioned there is a Rust crate that has implemented it. So we can compare and contrast mine to theirs, or maybe I'll just show you theirs. I don't know exactly what we'll do with that, but show you how it works so you can get an idea of how Stoyer-Wagner works. Again, that one was what was it doing? Node concatenation. It was like merging nodes. I'd have to go look at the details. I don't remember what it was. to like help find like those critical paths. So we'll do that in another video. But again, if you have anything else you want me to talk about, I'll keep adding cool topics to the list, either from my own mind or the things that you guys mention. Again, grateful for all your input, and everyone have an amazing day. Talk to you later.